And now we have our nucleophiles. Okay? Big thing to remember, get your definitions nailed down. Okay? If you get nothing else on this slide, what you need to be able to get is that nucleophiles are electron donors. Everything you do in the case, or all those extra things that are written down there and are now all scribbled out, is all in support of nucleophiles being an electron donor. Okay? So keep that in mind when you go through and look at these. Okay? The whole point is to have electrons. Okay? So where we find those electrons then becomes kind of questionable. Okay? The best choice is looking at lone pairs or pi bonds. Okay? Well, lone pairs because they aren't currently involved in a bond. Okay? They're just chilling on an atom. Those tend to be a great source of electrons, okay? Or donatable electrons because they aren't being used on anything else. The other option is going after pi bonds, and that's because pi bonds are higher energy and we have a weak overlap with another orbital. That weak overlap can be broken given the proper circumstances. So those are our two big sources for donatable electrons when we're looking at our nucleophiles. After that, we want to think about, well, what's going to make it a better nucleophile? Okay, well, negatively charged. If it's negatively charged, it has so many electrons that it is actually negative. Well, the whole point of a nucleophile is to donate electrons. I got a bunch of electrons, I can do that. Okay? So if we go through to take a look at some of these examples that we've got here, hydroxide is a better nucleophile than water because, well, it's negatively charged. Sulfide is a better nucleophile than H2S because it's negatively charged. Okay? Ammonia is a worse nucleophile than amide because, well, the amide is negatively charged. Okay? So as a general rule, it's better to be negatively charged as a nucleophile. Okay? If we continue to move through, the next rule that we would move to, interestingly enough, is not looking at size. Okay? And that's because size is this weird nebulous thing that has a huge solvent dependence, and that makes it really confusing. Okay, so I know we're breaking from our pattern of looking at charge, size, electronegativity, resonance, and inductive effects. Okay, but I'm breaking from it for a reason here. This is an easier pattern, and it's also the more standard pattern. So within this box that you're looking at, that big red box, those are the big rules you need to nail down. So donatable electrons, do you see them? Okay, negative charge, and then lower electronegativity means more nucleophilic. Okay, which you may be going, well, wait, but I wanted to have electrons. Okay, aren't electronegative atoms going to have electrons? Well, yes, and in a neutral situation, okay, methane doesn't have electrons, but water does, so water is a better nucleophile. Okay, but we're now saying they're both charged. Okay, so if we look at our examples, we're saying oxygen versus fluoride. Well, they're both negatively charged, and while fluorine is more electronegative than oxygen, how is that going to contribute to the nucleophile ability? Well, again, what's the definition? Our nucleophile must be able to donate electrons. If fluorine is more electronegative than oxygen, what is it doing to the electrons? It's actually holding them. The whole point of the nucleophile is to donate them. So fluorine becomes a horrible nucleophile because, well, it wants to hold its electrons. So our lower electronegativity, assuming the charges are the same, is actually more nucleophilic. Okay, which becomes interesting when we look at the classic one that students get confused, say ammonia and water. Which one is more nucleophilic? And you say, oh, well, oxygen's more electronegative, so it's holding more electrons. Exactly right. It's holding more electrons. What is the definition of a nucleophile? It needs to donate electrons. So when we go through to compare, we have to go through and follow through each of these rules. Okay? Find your donatable electrons. Negative charge is better than neutral. Okay? And then look at your electronegativity. So when we look at our nitrogen and our oxygen, we may be both looking at those saying, well, there's no electrons. Remember, implied lone pairs. Oxygen may have two lone pairs, but that doesn't make it negatively charged. Okay, so they both have donatable electrons. And at any given instant, you can only donate one pair. So it's kind of irrelevant that oxygen has two. So rule 1 is the same for both. negatively charged. Well, neither of them are negatively charged, so rule 2 is irrelevant. The next part is looking at our nucleophilicity with electronegativity. Okay? Lower electronegativity means more nucleophilic. Well, oxygen is more electronegative, which means the nitrogen is more nucleophilic. Okay? And that's because oxygen is holding those electrons. It's not willing to give them up. And again, back to our definition, our nucleophile must donate electrons. It must give them up. If it doesn't give them up, it's not going anywhere. Okay? Those are your 3 big rules that you're going to see all over the place. Okay? The next part is kind of in your harder ranking systems. Okay? The size dependence on your nucleophiles has a really strong solvent dependence. Okay? And some elements will even spin off and do all sorts of weird, crazy stuff after the fact. Okay? And this is a very tricky concept to get down. So at this stage, it's probably best just to memorize it and hope I only ask one question, which more than likely, that's all I'll ask. Okay? In a polar protic solvent, the bigger the nucleophile, the more nucleophilic it is. Okay? So protic, bigger, better. In an aprotic environment, smaller becomes more nucleophilic. Okay? And we'll look on the next slide on what's going on with it. If we go to no solvent, okay, where you're not given any information about the solvent, the bigger it is, the more nucleophilic. Okay? And this may seem kind of counterintuitive to our ranking of charges. Okay? And where this is coming from is this term polarizability. Okay? It's so big that the electrons can polarize to one side of the molecule, which is what we really need to have happen. The electrons need to shift to one position so that they can act as a nucleophile. They can donate out. Okay? So again, with size, very, very tricky. Watch out for it. Okay? The next one that is tricky has to do with steric hindrance. Okay? The less atoms around it, the more nucleophilic. Okay? Which is another one that we'll look at in a second, because that overlaps with our countering definition, bases. Okay? So those are our big rules. Try and get those nailed down. We'll take a look at some examples for our harder rankings. What's happening with size? Okay? So let's take chloride versus bromide. Okay? Our halides seem to be the best to figure this out. Okay? So let's again go back. Okay? In our protic environment, bigger, more nucleophilic, aprotic, smaller. So if we take a look at our solvent here, we're looking at our protic, in this case, and our aprotic here. Okay? So we've summarized our rule behind this, and we want to see what happens in each of these cases. So when we're looking at a protic solvent, okay, it's really less on the size and more on electronegativity. Okay? Chlorine is more electronegative than the bromine. So when we're looking at a protic environment, the interaction between our positively charged hydrogen and our now more electronegative chlorine now becomes relatively strong. Because bromine is not as electronegative, the hydrogens don't interact quite as strongly with the bromine, so we get a weaker interaction here. Okay, well, what's the net result? Okay, if I get a strong interaction with the solvent, what happens to the nucleophile? Okay, the nuke becomes weaker. Okay, because the nucleophile needs to share electrons with something other than the solvent. If it's sharing with the solvent, we're kind of screwed over. Okay? What happens when we look at the bromine? Well, if it's a weaker interaction, then in comparison, the nucleophile becomes actually not as weakened, which effectively means stronger. Okay, so our bromide ends up being the stronger nucleophile in a protic environment. What happens when we move to an aprotic environment? Well, in the aprotic environment, we don't have the large partial positive of our hydrogen bonding interaction. Okay? Where our positive is now actually buried inside the structure. Okay? And that makes it very difficult for that positive to actually get out and appropriately align with our chloride. Okay? or to appropriately align with our bromide. Okay? So now we don't get this big kind of stabilizing effect that we would get in the protic solvent. Okay? So now what it comes down to is, well, if we don't get that stabilizing effect, now how do we decide between these? Okay? Well, what happens with a larger atom? A larger atom means more solvents molecules around it. Well, if there's more solvent, what has to happen for the nucleophile to get out and react? Okay, well, it has to break those solvent interactions. Even though they're weak, there's more of them. So more of them must break for the bromide to react. Chloride being so small, well, it's got relatively minimal interactions, or fewer of them, so it actually has to break less interactions, and that makes the chloride a better leaving group because there's less things in the way. Okay, so this is less, if we wanted to call it, I mean, it's kind of weird to call it this, but we could call it less steric hindrance. Okay, which makes it the better nucleophile. Okay, ultimately what you need, the definition. You have to know the definition. Okay, so keep that in mind. I might ask you to explain it to see if you really know what's going on. I might not. We'll see. The next part, nucleophile versus base. Okay, and a lot of people have been getting confused with our definitions, and that's because if we look at the Lewis definition that overarches over both nucleophiles and bases, what is it? Well, they donate electrons. Okay, well, that kind of sucks. It's the exact same definition. So let's expand on that. Our nucleophiles donate electrons to things other than hydrogen, whereas our base donates electrons to hydrogen. Okay? Because those definitions seem so similar, we actually end up saying our bases are proton acceptors. Okay? Because we thought that that might be a little bit easier to differentiate. Okay? Well, how is sterics going to play a role in this? If we go through and take a look at hydroxide, okay, relatively small, okay, negative charge, there isn't a whole lot of junk back here, it's just a tiny little methyl group. Okay, so that hydroxide has the ability to either react with the hydrogen, okay, or it could potentially react with the carbon, okay, in a substitution. Okay, so in one case we're doing kind of an SN2, in the other case we're kind of going our E pathway. Okay, well, what prevents the SN2? If we take a look at the substrate, would you say this is a valid SN2 reaction or a valid SN2 substrate? We look at our center carbon, 1, 2, 3 carbons around it. That is tertiary. Well, crap, that's not going to run in SN2. Okay, why not? It's sterically hindered. Okay, so does sterics play a role in differentiating between our nucleophile and base? Well, yeah. Okay, the smaller our species is, the more likely it can get into the backside of our reaction and act as a nucleophile. The bigger it is, the more difficult it is to get in and do that reaction. So what happens if we now focus on, say, just the negative charge? Well, if we look at our left structure, we said this is relatively small. As a small species, it can kind of maybe finagle its way up there with a little bit of finesse to act as a nucleophile. What happens with this big old large group out here? Now it comes up and it's got this big old chunk floating on the outside that then bumps up against this. Okay? Well, now the oxygen is sitting here trying to get up there, and we have this entire gap where it can't make it through. Okay? So the larger our species is, our negatively charged species, the less likely it can act as a nucleophile. So if we look at our structure on the left, this is actually a really bad nucleophile. Okay? And the structure on the right is actually a pretty good nucleophile. Okay? They're both negatively charged, okay? And we could go through all of our rules, but it's really going to come down to size to differentiate between these two. Okay? Well, what happens if we now flip this over to our base definition? Okay, well, the one on the left, it needs to react with a hydrogen. Well, the hydrogen's on the outside of the structure. Okay, so that's really easy. Okay, I don't really care about size when I'm looking at base, okay, because, well, I'm reacting with something that's readily available. If we go through and look at the other one, okay, well, Well, I don't care about size because, well, it's reacting with a hydrogen on the outside of the structure. So the one on the left is a good nucleophile and a good base. The one on the right is a bad nucleophile because it's so big it can't get in to react, and it's a good base. How can I use this to differentiate? Okay, well, if I want a base, I don't want to use the species on the left because that will also act as a nucleophile. I'd rather use the species on the right because it is a bad nucleophile and it's still a good base. Okay? So thinking about the definitions on what these things are actually sharing with is a good way to go through and approach this. Okay? Some other species, this big old guy, DBN or DBU, something like that, tends to be a classic good nucleophile. Okay? Or sorry, good base. Okay? And it's a good base because it is sterically hindered. Okay? It has so much bulk and carbon junk around it, it can't actually react as a nucleophile. It ends up being a really good base, which is pretty awesome. Okay? So if we go through and take a look at this, we've got some common nucleophiles that you can see popping up here. Notice within our good nucleophiles that our textbook is referencing, you get a lot of negatively charged nucleophiles. Well, those are all relatively good nucleophiles because, well, they're negatively charged. Okay? And they're trying to show these in kind of a ranking. No, they're not, actually, so ignore that. Okay? If we go through and look at our neutral nucleophiles, all of those species act as decent nucleophiles because, well, they all have lone pairs. Okay? So these are all just kind of common things that you could see act as nucleophiles. Some of them are better than others. Typically, the more negative, the better off you are. Okay? Oh, sorry. And that is pretty much it when it comes to our nucleophiles. Okay? I will draw your attention to the halides can only act as nucleophiles. So one of the things that we had kind of neat is that we could use bulky negatives only acted as bases. Okay, well, what can we have act only as nucleophiles? Well, it turns out halides are now the flip. Halides can only act as nucleophiles. I wonder why that is. Why can a halide not act as a base? I wonder what it produces that would say that's not going to happen. It's a good question. You should probably answer that by Monday.